Hey man, let's do an example of single-stage liquid extraction. So here's the posted notes. Please absolutely have the PDF file with you and open so you can look at it. So problem number 1, make sure you have read the handout on liquid extraction, excerpt from tray bell and mass transfer operations. Absolutely. Number 2, contemplate for 16 hours how insensitive you have been toward Elroy's pet mushroom. Clearly some backstory here. Not sure what's going on with that question, but so let's just go to question number 3. So 100 kilograms of a binary mixture. It's 45% acetone. That's the solute that we're interested in. 55% water, which is the diluent. And we'd like to extract the acetone from the water. And it is mixed with pure MiK. That is the solvent. So question A is, if the amount of MiK used is 60 kilograms, the resulting ternary mixture will split into 2 phases. What are the masses and compositions of the raffinate and extract phases formed? So that's a perfect example of us wanting to know what comes out of a liquid extraction. And then it says phase diagram is given on a separate sheet. And the separate sheet is that one. So this is the mass fraction of MiK, the solvent. This is the mass fraction of acetone, the solute. And those are the data that were given. So let's look at the solution. Okay, solution for problem number 1, reading that interesting handout. Solution number 2, not quite sure what's going on there. Okay, solution number 3. So we see here A, water, diluent, C, acetone solute that we're interested in, B, MiK, the solvent that we're using. The first solution, or the feed solution, is 100 kilograms. XB is equal to 0. It has no solvent, no MiK in it. And as we said in reading the problem statement, the acetone mass fraction is 0.45. The second solution, or the solvent entering, is pure MiK. So XB x MiK is 1, and it has no solute, so XC is equal to 0. In part A, we were using 60 kilograms of that solvent. So I want to locate the mixture point M. So if I calculate the C mass fraction, that's what I'm doing over here. It's the 100 kilograms times the 0.45 in the feed solution, 60 kilograms times 0, C coming in with the solvent. Total mass is 100 plus 60 is 160, so you get 0.281. So one way of characterizing the mixture, the overall mixture that results from mixing the feed or the first solution with the solvent or the second solution, is that it should lie on the straight line that joins the F and the S solutions, and the C mass fraction should be 0.281. Alternately, I can calculate the B mass fraction. Counting B, we have 100 kilograms of the feed. That actually has no B in it, so that's a 0. 60 kilograms of the solvent. That's actually all MiK, so that's a 1. All B, all MiK. Again, the total mass is 160 kilograms. So the B mass fraction of the overall mixture that results is 0.375. So we could equally well go on the line that joins the feed and the entering solvent and find that place where the B mass fraction, or the horizontal coordinate, is 0.375. Or we could just use this as the vertical coordinate, this as the horizontal coordinate, and locate that point. So let me fast forward here. Oops. So here's the feed solution, the entering solvent, and by one of those 3 ways we located the mixture point M here. Now, does that mixture exist like that? No, it's inside the 2-phase region, so it splits apart into 2 phases. In the past, I've called them R for the A-rich raffinate and E for the B-rich extract. That's fine. Actually, here I'm using other common notation. The raffinate phase is oftentimes called L, and in the future, especially in countercurrent contact, we will be using that notation, so I can also call it L. The extract phase is also traditionally called V, and that doesn't mean it's a vapor. That's just a name now. It's just called V. So you can think of these as L raffinate leaving, V extract leaving, or you could go back and call this R raffinate leaving and E extract leaving. Really doesn't matter. In any case, so this mixture splits apart into this exiting raffinate and this exiting extract. So notice that here are some tie lines, and they're kind of drawn lighter. And here is the tie line that I have to the best of my ability interpolated between that tie line and that tie line. And on that basis, I conclude that this is the exiting raffinate, this is the exiting extract, and so you can read off the horizontal and vertical coordinates of that point and the horizontal and vertical coordinates of that point, and you get these results. So the exiting raffinate has 0.03 mass fraction MIK, B 0.215 mass fraction of acetone, C, and A is 1 minus those two. And the exiting extract has a B mass fraction, MIK mass fraction of 0.607, a C solute mass fraction acetone of 0.328, and so YA is just 1 minus those. So in terms of compositions, that's what comes out. Now, what are the masses of those two streams? So that's what I'm doing here. The overall mixture, first I thought of as representing a mixture of the entering feed and the entering solvent, and that's a certain total mass. But I can also think of it as what leaves, and what leaves is the exiting streams, the L and the V stream. And if I do a C balance on those, the total mass times the, for the overall mixture, the mass fraction of C is the total mass of C in the two leaving streams. So that's the total raffinate times a C fraction of that, plus the total extract times a C fraction of that. Do a little rearrangement here, collect all the L terms on the left, all the V terms on the right, and this is exactly the little bit of algebra I did in the lecture material. And so I come to the conclusion that the ratio of the exiting raffinate to the exiting extract is this difference over this difference, put in the numbers, 0.71. So I now know that raffinate over extract leaving is 0.71, which is fine. Alternately, you can also go by, you could alternately go by a B balance, and instead of using C mass fractions, do say all the same words, but instead use B mass fractions. And if I put in the B mass fractions, I get 0.67. So those two results are pretty similar. So I kind of split the difference and said, looks like from the graph, L over V is about 0.69. And then L plus V is the total mass leaving, which was the same as the total mass entering. And that's, has to be 160 kilograms. But notice I wrote L plus V as L over V times V plus 1 times V. So V is 160 divided by that number, which was, 1.69. So my conclusion is that the exiting extract is 95 kilograms and the exiting raffinate is 65 kilograms. So now I'm done with a single stage extraction because I have stated and determined not only the compositions of those two streams, but also the amounts of those two streams. Now let's go back up to the problem statement. And look at these interesting parts B and C. And this is kind of new. So part B here says, what is the minimum amount of MIK required to produce a mixture that separates into two phases? And part C says, what is the maximum amount of MIK that can be added such that the resulting mixture will split into two phases? So what's going on there? What's going on there is the idea that to do a liquid extraction, you have to get a mixture that splits into two phases. And so if I cut forward to the solution again, to this picture, I can imagine taking the feed solution and adding 1 drop of the solvent S. And the mixture point would be just scooched over a tiny bit from F. And then I could add more drops and more drops. And gradually the mixture point would move along the line like that. There would come a point where the mixture point first touches the two-phase region. And actually, to split apart into two phases, I have to be inside the two-phase region. So if I start from the feed solution and add more and more and more gradually solvent, the mixture point moves in here. This is the first time, so I've labeled it M prime here. This is the point where I first move into the two-phase region. Now clearly when I'm just inside the two-phase region, I'm mostly this solution here and almost none of this solution over here, but at least I split apart into two phases. You keep adding more and more solvent. The mixture point M that I calculated, this is where the mixture point was if we added 60 kilograms of solvent, MIK. Supposing I add more, the mixture point moves down here, down here, down here, keeps moving down. Eventually, if I add a whole lot of solvent, the mixture point gets to here, and then it exits the two-phase region. So the maximum amount of solvent that I can have corresponds and can add and still be two phases is that point there, which I labeled M prime prime. And if I add more solvent than that, I've passed out of the two-phase region, and again, I exist as a single phase. Clearly, if we have the feed and we add 1 trillion tons of solvent, it's a solution which is basically solvent, and it's clearly just one phase because it's outside the two-phase region. So for liquid extraction, if we happen to have these compositions of the feed solution, and of course the solvent is pure MIK, as I add more solvent, the mixture point moves. If I add 1 drop of solvent, the mixture point is about there. Keep adding solvent, keep adding solvent. Here's where I first pass into the two-phase region. I start splitting apart into two phases. As I add more solvent, I always split apart into two phases. For part A, when I added 60 kilograms of solvent, these were the two phases I split into. Keep adding solvent, adding a lot of solvent. Eventually, this is the last point where I still split apart into two phases, and after that, back to a single phase. So, to answer the questions, I have to determine how much solvent do you add to get to this mixture point, and then how much solvent do you have to add to get to this mixture point. Okay, so for this mixture point here, I'm just doing the mass balance, and the C mass fraction of this mixture point, M prime here, is equal to 0.401. I guess I read this graph very carefully, 0.401. And so I do this mass balance, the same mass balance, and solve for S, and S comes out to be 12 kilograms. So if I took the 100 kilograms of the feed solution and added 12 kilograms of solvent, my overall mixture lies here, and it's just starting to split apart into two phases. I do the same calculation, but with this mixture point M prime prime. And here, see, that mixture point has a much smaller value of XC. Again, I must have read the graph pretty carefully because that XC, the vertical coordinate of that mixture point M prime prime, was 0.026. And I do the same calculation, and I get 1,600 about. So if I keep adding solvent, I still split apart into two phases until I add anything more than 1,600 kilograms, and then I become a single phase again. So for liquid extraction to work, you always have to lie inside the two-phase region. And so I just get into the two-phase region as I add more solvent. When I add 12 kilograms of solvent, and I'm in the two-phase region for my overall mixture, that means I will split apart into two phases until I add anything more than 1,600 kilograms, and then I exist as a single phase. So the key thing is, or the key idea here, is that to have a liquid extraction to split apart into two phases, the amount of solvent you have has to lie or correspond to mixture points that lie between M prime, this one, and M prime prime, this one. And in part A, I chose 60 kilograms, and that brought me here. Yeah, and 60 kilograms is more than 12 and less than 1,600.